Hi folks, welcome to the 6.2 volume with known cross-section practice. So we're going to go ahead and get started here with question number 1. So with question number 1, we have a function. I know the picture's not very clear, so let me just write the function next to this. That the function we're looking at is the square root of x and let's say g of x equals the negative square root of x. And together, those graphs, these functions right here, make this sort of sideways parabola that you see there, okay? And though the picture doesn't tell us, I've decided to give it some ending points so we can calculate the volume, 4, 2 and 4, -2. Now the picture's drawn kind of slanted because we want to be able to see that the cross-section coming out of this base is a square. Okay, so this part right here is a square that's sort of standing up from this base that is shaped like the space between two parabolas. Another way to visualize this might be to draw our xy coordinate in a more traditional way, like the up and down way. And if we do that, we can take a look at our function. We can see that we have the square root of x, and then we have the negative square root of x, and that the cross sections are slices that go this way, so they are perpendicular to the x-axis, okay? And we're going to go ahead and stop at 4, 2 and 4, -2. All right. So in my diagram, you can't see the squares because they're standing straight up and down, but in the book's diagram, you can kind of see that square. All right. So let's go ahead and solve this question. So we're going to try and find that volume. And we know that volume equals the integral of the area, and in this case I know it's going to be dx because my slices are perpendicular to the x-axis. And I'm going to need a starting point and an ending point. And so if I go ahead and plug in the information I have, I know that I'm going to take the integral from 0, that's where my smallest square is going to be, all the way to 4, because that's the x value of where I want to stop. And then, because the shape is a square, I want to take the side length of the square, and I'm going to square it. That will give me the area. And I want to finish off with a dx. Okay, so let's figure out how we find our side length. So the side length, if I look at my diagram, is going to be this distance right here plus this distance down here. So it's going to be the whole distance between both curves. And that distance we can represent as 2 times the square root of x. And that is the side length. And so now we have to square it to find the area. And we're going to finish off with our dx. Okay, so now that we have our setup, and this is the most important part, is make sure you have the right setup, now we're going to evaluate. So I get the integral from 0 to 4 of 4x dx, which is the same as 4 times the integral of x dx from 0 to 4. Remember, I can take that constant out. Now I'm going to find my antiderivative. 4 times 1/2 x squared. Draw your vertical line, put a 4, put a 0. Go ahead and plug in our bounds. Actually, let's simplify first. So these 2 will reduce to 2. So I'm going to get 2 4 squared minus 2 times 0 squared. and that is going to give me 2 times 16, or 32. So 32, just to bring it back into context, represents the volume of this shape. Okay, so we integrated the area to find the volume. All right, let's take a look at question number 2. So in question number 2, kind of same thing, I went ahead and entered some endpoints so we would have some bounds to help us find the volume. So this time we're looking for the volume. However, the cross sections are not squares, but they are semicircles. And so when we draw sort of the sketch that looks maybe more traditional, we would have our y-axis, our x-axis, and then the graph is the same. I have the square root of x up here, and I have the negative square root of x down here. And I'm trying to find this part. So in this diagram, this line represents the diameter of my semicircle. Okay, so if I look on this diagram, I can see that that's the diameter, and that's what this line represents, is the diameter. Okay, so now that we've established that, let's go ahead and set up our equations. So we have the volume equals the integral of the area. Do I want dx or do I want dy? Well, I can answer that question by imagining if I kept drawing these purple lines, like this, and like this, and like this, they would be stacking along the x-axis, so I need to finish my integral with a dx. And now I'm going to go ahead and fill in my bounds and my equations, all right? So the integral from a to b, and let's think about the area formula for a semicircle. So we're not doing a square like we did in example 1, we're doing a semicircle, so we need a different area formula. And the area of a semicircle is pi over 2r squared, and I'm going to finish that with a dx. Now let's plug in the information we have. So I know I'm going to start at 0 because the x value right here is 0. I know I'm going to be finishing here, and that x value is 9. So I can put a 9 in for b. I'm going to go ahead and pull this pi over 2 out into the front because it's a constant. And now I just need to write the radius in terms of an equation. Well, the radius is going to be not the whole length here, but the radius is going to be half of it. And so that distance is dictated by the function, the square root of x. I don't need 2 square root of x like I did in example 1 because I'm only going half the distance. Okay, so now that we have our equation, let's go ahead and simplify. So pi over 2, the integral from 0 to 9 of x dx. All right, let's integrate. Pi over 2, 1/2 x squared, draw the line, 9 and a 0. All right, let's bring all our constants together. So pi over 4, 9 squared, minus pi over 4 times 0 squared. And I know my last term is going to go to 0, but my first term will give me 81 pi over 4. And 81 pi over 4 represents the volume of the shape when each cross-section is a semicircle. All right, so folks, we're going to stop here for the practice. Come on back to see a video of example 3 and example 4. See you there.